Hello everybody, welcome back to another video, and in this video we'll be looking at taking the derivatives of the inverse trigonometric functions. And this will be my first video on this topic, as I'll be making multiple videos where each video will be dedicated to taking the respective derivative and integral of the inverse trig function. So in today's video we'll be looking at taking the derivative of the inverse sine of x. So what we'll be doing is we'll be using key ideas and a key method, namely implicit differentiation. And what we want to do with implicit differentiation is we want to find dy by dx, because what we do is we set up some function y, because we're often differentiating a function of y. So we're saying that here y is the inverse sine of x, I can denote it as. And what we want to do is we want to find dy by dx, because by taking d by dx on both sides, we see that the left hand side we get dy by dx, and on the right hand side we get the derivative of sine x, inverse sine of x with respect to x. So what we do now is we need to see that if we take the derivative on both sides simply, that won't help us, because we'll need to know the derivative of the inverse sine of x, which is what we're trying to do. So what we'll need to do now is we'll need to know that by taking the sine on both sides, so let's say we take the sine on both sides, so the sine here and the sine here, we know that the sine of the inverse sine of x will just return x by definition, because the inverse sine of x will take a triangle where the ratio of the opposite and the hypotenuse is x over 1, and taking the sine of that will just return exactly that. So that's why they cancel out. So what we see here is that the sine of y is just equal to x. So that is pretty cool. And what we can do now is we can actually take the derivatives on both sides, because they are much easier to do. So let's try taking the derivative on both sides, and by that I mean more specifically taking d by dx. So if we take d by dx on both sides, we see that, let's just do the right hand first. The derivative of x with respect to x is, yes, our favorite, just 1. And on the left hand side, we're taking the derivative of a function of a function. And yes, that is the perfect call for the chain rule, because we know the chain rule takes in where, for instance, you have maybe some secant x to the power of 2, and taking the derivative of that, you need the chain rule, or taking the derivative of the sine of the cosine. Here, we know that y is definitely not a constant. Y is in fact a function of x. Y is defined to be the inverse sine of x. So when taking the derivative of sine of y, we need to make sure to use the chain rule. So what do? We take the derivative of the outer function, so that is derivative sine, which is cosine y that we know, then multiply by the derivative of the inside. Now the derivative of y with respect to x is dy by dx, and what we see is that we want to isolate dy by dx, and we have a dy by dx here. Now how do I isolate this? Well, we divide by cosine y on both sides in order to get dy by dx on its own. So we divide by cosine of y. So here we see that dy by dx is equal to 1 over the cosine of y. Now what we can also do is we can use the fact that the 1 over cosine, the reciprocal of the cosine, is exactly the secant of the input. So now we see that the dy by dx is just equal to, now we have the secant of y. Now what is our y? Our y is the inverse sine of x. So what we can do is we can get an expression completely in terms of x and then construct a triangle. So what I mean by that, we see that dy by dx is equal to the secant of the inverse sine of y. Now whenever we have, so we have the inverse sine x. So whenever we have a trig function on the outside, and inside we have an inverse trig function, so that would mean like a trig function of an inverse trig function, what we can do is we can always simplify this by drawing a right-angled triangle. And what do I mean by that? Well, we know the inverse trigonometric functions take in a ratio of side lengths as an input and spit out an angle. And by definition then, we're taking the inverse sine of x, which means that the ratio of the opposite and the hypotenuse, as per the definition of sine, must be x over 1, because we know that x is the same thing as x over 1. So therefore, we can construct a right-angled triangle where the opposite and the hypotenuse are of lengths x and 1. And of course, by Pythagoras, we know that this side here will just be c squared minus b squared, which is 1 squared, which is just 1, minus x squared. So we have the square root of 1 minus x squared. So what we can do now, we see that this is the triangle that is produced with the inverse sine of x. And what we're doing is we're applying the secant function to this triangle. So this angle, let's say here is theta, and this inverse sine of x will return the angle theta by, of course, taking in the opposite and the hypotenuse. Then taking the secant of theta will just be taking the opposite, the hypotenuse over the adjacent of this triangle. So we see that dy by dx, the derivative of y with respect to x, is just going to be equal to the secant, which is the hypotenuse over the adjacent, which is 1 over the square root of 1 minus x squared. And this is where we get our famous derivatives of inverse trigonometric functions. And we can see that we will always get cases where we can simplify the trig function applied to an inverse trig function because we can construct a triangle. But remember, not the other way around, because if we're taking the inverse trig function, so let's say we're taking the inverse sine of secant x in this case, we would not be able to do anything because the secant of x, well, this x takes an angle theta, and we have a theta here, and taking the inverse sine of just a secant function, we don't have enough information. So what we need to often have is have it in a structure like this, which will be how we take the derivatives of the other inverse trigonometric functions. So that was I think a good introduction to implicit differentiation, and now we know how to derive the derivative of the inverse sine of x geometrically as well. So that was it for today's video, and thank you for watching.